Hi, sir. Shall we start, sir?
Yeah.
Yeah, I am CB. I'm presently head of the Department of Physics. So let me give you a formal welcome for the gathering. Sir, I will take only 1 minute. Welcome all to the Luminary Lecture Series organized by Department of Physics, University of Kerala. Today we have Prof.Niel Alford to be our chief guest. He is an eminent scientist in the field of material science. Since we are celebrating our 50th year of existence, we are privileged and honored that you accept our request and is ready to deliver an invited talk on mobile phones, Russian dolls, room temperature mazes. And I personally feel that it is a very interesting title too. So we are now a group of 40 plus research scholars, 60 PG students, and right now we are pursuing mainly material science as our research. So on behalf of all who have gathered here, I extend my sincere welcome to Professor to this gathering. Now I welcome all the dignitaries, faculty members, teachers, research scholars who are joined in this online platform. I now give the charge to Dr. Subho to convene the session. Subho sir, please carry on.
Thank you, CB. Now I invite our research scholar, Ms. Sarika, to formally introduce the speaker.
Thank you, sir. A very good afternoon to one and all. As part of the 50th anniversary celebrations of the Department of Physics, University of Kerala, we have organized an invited talk by Prof.Niel Alford, Associate Provost, Imperial College of London, UK. He is an eminent scientist in the field of material science and engineering, who is an expert in masers, quantum engineering, microwave dielectric materials, high temperature superconductors, and ferroelectric thin films. Professor Alford received his BSc from St. Andrews University and spent 3 years working in Southeast Asia and South America in the oil exploration industry. He returned to the UK to carry out his PhD at Queen Mary College in the area of fracture mechanics of cement mortar. He carried out postdoctoral work at Oxford University in collaboration with ICI, developing high-strength cement. He joined London South Bank University in 1994, and his work on microwave dielectric materials there has been patented and transferred to industry. In January 2007, he and his research group moved to Imperial College in London. In 2011, the research activity by him and his colleagues led them to the discovery that it is possible to construct a maser operating at room temperature and in the Earth's magnetic field, which got published in Nature in the year 2012. The diamond maser is expected to find uses in quantum sensors and navigators and in quantum communications, and early applications are envisaged in low noise amplifiers. He is a recipient of several awards, including the prestigious Griffith Prize and medal in 2008 and the Platinum Prize in 2018. In 2013, he was awarded the MBE for services to engineering. He has served as head of the Department of Materials and vice dean in the Faculty of Engineering in the Imperial College, London. He is currently the associate provost for academic planning there. He has around 22 patents and 250 publications in internationally acclaimed top journals, out of which more than 10 were published in Nature. It's an absolute privilege to have Professor Niel Alford on this occasion to deliver a talk on mobile phones, Russian dolls, room temperature mazes. With great pleasure, we welcome you.
Well, thank you very, very much indeed for that wonderful introduction. And let me say what a privilege it is for me to be able to give you this talk today on your 50th anniversary. And it's a personal pleasure too to meet up with some colleagues of mine, Subodh, and in particular, Sebastian. I'm delighted to have had a quick chat with Sebastian before we started, and he hasn't changed one tiny bit. So I'm going to try to present this now, so please let me know if this is working. Okay. Excuse me, that's not working. I wonder, can you see that?
So far, no, Professor Alford.
Just let me know if you can see my. Can you see that? Hang on a sec. Okay, just.
No, not yet.
Okay, well, hang on. Let me just try and figure this out. Okay. Sorry about this. Can you see this yet?
No.
No? Oh dear, hold on. Let me
No,
see if I
no,
can get this.
no.
Okay, hang on. Let me cancel that.
Earlier,
Okay. Yeah, I managed to do it earlier. I'm just trying to figure out how I did that now. So,
go to the present now button and then.
I need to find my. Okay, so I've opened up my presentation. I then go to the present now button, yeah?
Yes.
Okay. Here we are. Right. Now, can you see that?
No.
Can you see that?
Now it's coming. Now it's coming.
Oh,
Yes,
great.
yes.
Okay.
Yes, it's coming.
Okay, well, I've got over the first hurdle. So, as I said, I'm absolutely delighted to be able to give this talk today. And the talk is going to be on mobile phones, Russian dolls, and room temperature masers. So, first of all, I'm going to talk a little bit about microwave materials and dielectric resonators. Then I'm going to talk about ultra-high Q factors and the way that we manufacture that with in a sort of Russian doll arrangement. And then I'm going to talk about the room temperature maser. So, as you know, a microwave dielectric is an insulator, and it has the ability to confine microwaves because it has a higher relative dielectric constant than free space. The thing that we're particularly interested in this talk is the quality factor of the resonator. And a resonator is a little bit like a tuning fork. If you hit a tuning fork, it will ring for a long time. And if you hit a dielectric with microwaves, again, if it rings for a long time, then it means it has a high Q. And that is what we're interested in. And we use dielectric resonators every single day. We use them, for example, in a quartz watch. So it's a little bit like a quartz watch, but the critical factor, as I said, that we're interested in here is the quality factor or the dielectric loss. Now, just very briefly, I'd just like to explain why we want to increase the Q. And if we're going to understand how to increase the Q, we need to understand a little bit about the theory of dielectric loss. Now, dielectric loss is caused by an anharmonic system of interactions of photons with the phonon system of the material. The field frequency is much, much lower than the transverse optical phonon frequency. And really, the things that we're particularly interested in is the acoustic transitions and the acoustic optical branches. The harmonic interactions give us the dielectric constant, the sound velocity, and the bulk modulus, but it's the anharmonic interactions that give us the dielectric loss that we're interested in. Now, Gurevich, Herring, and Tagantsev all produced theories of dielectric loss. They were mainly based on the work of Conyers Herring back in 1937 and 1954. And what we can see here is that the dielectric loss should go as a fifth power of the temperature. And so if we have a look at that, we can see that it can describe the temperature dependence of the dielectric, but not the absolute value of the loss. And so we need to start looking at how we can manage that. What we also find is that the theory of loss does not, this particular theory does not predict the absolute value for the dielectric loss or the tan delta very accurately. And that's because the symmetry is broken. So we need to model the key properties. And what we've done is to use a material, magnesium oxide. This is a good material to use because it's a fairly simple material. It's a simple face-centered cubic structure, and it's very popular substrate for growth of advanced oxides. So here is the single crystal of magnesium oxide, and here is the relative permittivity. And there's a nice smooth curve, the relative permittivity. And here is the loss tangent for the same single crystal at around about 10 gigahertz. And we see that there are some, it's not as smooth as the one that we had before. And this is due to defects and impurities in the single crystal itself. And then we can also look at the temperature coefficient of permittivity. So these properties are fairly straightforward, but this property is not so easy to predict. So thermal expansion, pretty good agreement. That's not a problem. And then we need to look at the phonon density of states, the difference and summation processes. And for the loss, only the difference processes are important here. Now, the optical phonon self-energy, this line width is proportional to the loss. So this can give us a clue about how we can start to predict the loss itself. So we can look at the phonon line width of the material. And what we can find is that we have excellent agreement with the temperature dependence of the tan delta with theory. And so, and I should say that my colleague Jonathan Breeze developed this theory during his PhD. And of course, Sebastian will of course remember Jonathan quite well, I'm sure. And so what we have is pretty good agreement at room temperature for the dielectric loss of polycrystalline and single crystal sapphire and alumina. And here we've got the reference to Jonathan Breeze's PhD thesis. So at last we have a means of looking at the imaginary part of the dielectric constant, the dielectric loss, and we have a handle on how to predict it. Okay, so now I'm going to talk about the quest for a very high Q material. And here we've got a dielectric resonator, which is, for example, sapphire at 10 gigahertz inside a hollow metal cavity. And the Q of this would be approximately 50,000 at 10 gigahertz. The whispering gallery mode can give us a much higher Q because there's a confinement of the energy within the dielectric. And here, the Q is then limited by the dielectric loss in the dielectric itself. So how do we beat this dielectric limit? Well, this is where we come on to the Russian dolls. And here we've got a whispering gallery the very high Q that I showed you before. This is the Whispering Gallery in St. Paul's Cathedral, actually. But what we wanted to do was to confine the mode energy within the air, not within the material, within the air, to see if we can then increase the Q above the dielectric Q. And so this is some work that we did with Jerzy Krupka in Poland. And what we found was that if we were to model a spherical aperiodic Bragg reflector resonator, if the shells of the system of the Bragg resonator are identical, in other words, if they are equal, then we get a saturation of the Q factor, and that is the Bragg saturation. But if the shells, the layers, are aperiodic in thickness, then the Q can increase asymptotically. And so this is what we tried to look at and to try to make. And so what about, we can't make nested spherical resonators, that's impractical, but what about nested cylinders, a little bit like this Russian doll? Well, this is what we spent a year looking at. We had a small grant to look at the cylindrical reflector resonators, and we did this at 30 gigahertz. And the predicted Q at 30 gigahertz for a Bragg, that's the equal thickness, was 245,000 for the Q. And for the aperiodic resonator, this went up to 650,000. So that was the predicted Q. Well, we made this in sapphire. The sapphire wasn't particularly great sapphire. It wasn't particularly pure, but it was what we could afford, actually. So here is the beginnings of the reflector resonator inside a copper cavity. And here we see the reflector resonator being constructed inside its cavity. And the result was a very, very high Q of 600,000, very close to the predicted at 30 gigahertz. So with a Q that high, what we began to ask ourselves is, what could you do with a very high Q? Well, we could make clocks for frequency standards. We could use them for positioning systems. But then we wondered whether we could make a very high Q work within a solid state maser. And so if we could exceed the threshold for masing by confining the energy with this very, very high Q, could we make a solid state maser? Now, excuse me, I'm going to talk about the maser itself. The first maser was built by Townes, Gordon and Ziegler at Columbia University in 1953. And as you can see, there it is, there's Charles Townes. It's a huge, huge piece of kit. And it has very specialized and rather limited uses: atomic clocks, very low noise amplifiers in radio telescopes, and for deep space communications. Now, amplification by stimulated emission of radiation relies on a population inversion. Here we have an incoming photon. The stimulated emission electron drops to the lower state, like that, and that emits an additional photon. The stimulated emission, 2 electrons drop to the lower state, and that emits 2 additional photons. 4 electrons drop to the lower state, and so on. Emits 4 additional photons. So this is the stimulated emission of radiation, and this is at microwave frequencies. So why are we interested then in masers? And the main reason is because they offer incredibly low electromagnetic noise, and we all experience problems with electromagnetic noise. It's a little bit like trying to hear your child across a very noisy playground. The sound of all the children around is very difficult to pick it out. And we've all experienced problems with noise in our mobile phones, for example. So noise is the thing that we really need to look at. And this is what we're trying to do. On the left, you see the low signal to noise ratio, and that's very noisy. And what we want to do is to amplify the key signal that we're looking for to get a very high signal to noise ratio. That's what we want to do by the application of these radio or microwaves. Now, a remarkable example of the use of a maser was the Mars rover, 140 million miles away. The radio transmission from the Mars rover to Earth was amplified on Earth by a maser to retrieve that tiny signal that came all the way from Mars, 140 million miles away. The problem is that solid-state masers need very, very big magnets, the masers that we use today, very big magnets, and they need cooling with liquid helium. And of course, you can see that the liquid helium transfer to this is incredibly inconvenient. So the reason that masers were overtaken by the laser is because the laser didn't need cooling. It could be miniaturized and it could be mass produced, whereas the maser was too bulky, it needed cooling, and there was absolutely no prospect of mass production. So there we go. On March 22nd, 1960, Schofloff and Towns were issued the patent for the laser, and that really meant that the maser was confined to really a piece of interesting science. So we started looking at organic materials to try to make a maser that worked at room temperature. Now, organics are generally very low melting point, mainly carbon and hydrogen, and we used pentacene, which is a polycyclic aromatic hydrocarbon with 5 benzene rings. It's also pretty well known as an organic semiconductor. It does have a slight problem. The melting point's only about 300 Celsius, so we can't illuminate it with a laser for very long. Now, the idea of organic masers is not new. The first attempt to do this was in 1961. And then the most recent attempt, before we did the maser, was in 2002 by Aaron Blank and colleagues at the Hebrew University of Jerusalem. And what they said within this paper was that the classical spin polarization mechanisms, such as the triplet mechanism, are not suitable for maser operation at room temperature. In other words, it wouldn't work at room temperature. So what we did was my colleague Mark Oxborough worked with us for a year on secondment from the National Physical Laboratory, and Jonathan Breeze and Mark Oxborough and myself started looking at this pentacene, and we made the pentacene by a single crystal growth method, and we encapsulated it in another polymer called p-terphenyl. And the result was the first solid-state room temperature maser. And what you can see here is that we illuminated it with a pulsed dye laser, which we bought second-hand, and put it inside a copper cavity. And there's the copper cavity, and the pink thing in the middle is the pentacene within the terphenyl. And what we then put that around that, we put around a very high Q sapphire resonator. And the result was that we were able to make the first room temperature solid state maser. And the advantage is, of course, that there's no moving charge, there's no semiconductors, just free electrons. Now, the key challenges that we face is that we wanted to reduce the optical pump power because it was too high. The pulsed dye laser had a 2 kilowatt peak power. we needed to miniaturize it. It was quite bulky, 20 centimeters in diameter. And we wanted to be able to manage it continuous wave mazing, not just pulsed. At the moment, we could only make it in pulsed mode. And this was our roadmap. On the left, you see the pulsed dye laser, and we could see that we have a rather large apple, roughly the size of an apple, the sapphire resonator. We were then able to miniaturize that a little bit using strontium titanate, and then we wanted ultimately to be able to put an LED pumped split ring resonator onto a chip. So how can we improve the maser? Well, there are three factors that contribute. Optical pumping, the efficiency, the power and the wavelength, the characteristics of the triplet states, and that's the quantum yield, and most importantly for us, the magnetic Purcell factor, which I'll just talk about now. So this was the key to miniaturizing the maser itself. And what you can see here is that really the Purcell factor is the quality factor of the resonator divided by the magnetic mode volume. And so what we want to do is to maximize the Q factor and to minimize the mode volume itself. And we were able to do that using strontium titanate. And you can see that the magnetic mode volume, even although the Q factor is only 10,000 compared with 170,000 for alumina, the Q factor of strontium titanate is only 10,000, but the magnetic mode volume is very small and the Purcell factor is very high. And the Purcell factor is the critical metric that we require in order to see how we can make this threshold for mazing. And so here is the miniaturized strontium titanate maser. You can see we've got optical pumping in a very small copper cavity, and we can see this beautiful result, still using a flash lamp, but the pumping threshold went from 2 kilowatts to 20 watts. So this is certainly moving in the right direction. What we also found when we were doing this was that we were able to observe very, very strong quantum oscillations or Rabi oscillations at room temperature. And so this was a very exciting observation and interesting for all sorts of quantum applications. So we were able to miniaturize this quite well, but there's a problem. We can't use it in continuous mode because the organic pentacene, first of all, the spin dynamics do not permit continuous operation, and the organic simply fries under the continuous wave illumination. So, can we make a maser work continuously with pentacene tertaphenyl? And the answer is no, because there's a bottleneck. So, the spin dynamics do not allow us to do this in any case. And also because almost all of the optical pump power is converted to heat, and the thermal conductivity of the petite tertaphenyl is very poor, we have a low melting point, and the organic simply melts under the maser power. So organics are unsuitable at the moment. Still okay for pulse mazing, but not for CW. Okay, so what about inorganics with suitable spin dynamics and higher melting points, such as, for example, diamonds with nitrogen vacancy defect centers? So let's go back to the fundamental question. Why do ruby masers need cooling? Well, because the spin lattice relaxation is so fast. And at room temperature, the spin lattice relaxation is less than a picosecond. So that is the problem. It's the real big problem. And so what we needed to do was to find inorganics with a much longer spin lattice relaxation. And what we found was nitrogen vacancy defects in diamond have quite long spin coherence times of the order of microseconds. They also have ground state triplet with slow spin lattice relaxation of milliseconds, not picoseconds. And of course, they have fantastic properties, mechanical and thermal properties, with a thermal conductivity of 10 to the 4 watt per meter Kelvin. Now, going back to the literature, we find that nitrogen vacancy defects in diamond had been thought of before, in fact, in 1977. And there was a suggestion that this phenomenon could be used to construct a maser operating at room temperature. Of course, it was never made, but there was a suggestion that it could be. And so we built a high Q cavity. That you see the copper cavity there, and we have a small sapphire resonator, which has a loaded Q of 30,000 and an unloaded Q of 56,000. And we calculated that that Q, with the Purcell factor that the sapphire offered us, would give us the threshold for masing. And you can see that we put the diamond inside the sapphire ring, right inside the high Q cavity. And so here is the setup. You can see the little red diamond inside there. And actually, it really is red because of the nitrogen vacancy defects. And this is the very first observation of continuous wave maser emission. It was at 9 gigahertz. The power was about 10 picowatts. The line width was 50 hertz. And the spin temperature, and this is very important actually, is about 2 Kelvin. And a very low pump power, I should say, of about 400 milliwatts, much, much less than we had for the previous maser. And so this was published in, the first one was published in Nature, and the second one was also published in Nature. Now, one of the very important metrics, I'm close to the end now, but one of the important metrics is the noise temperature. In 1960, the Ruby maser, operating at 4 Kelvin, had a noise temperature, amplifier noise temperature of 20 Kelvin. This was improved with the traveling wave tube Ruby maser to 2 Kelvin for the amplifier noise temperature at an operating temperature of 4 Kelvin. Today, the best noise temperature would be a semiconductor indium phosphide high electron mobility transistor, and that was measured in 2003. Again, the noise temperature is 2 Kelvin, but look, the operating temperature is still 4 Kelvin. Now, the Pentacene maser and the diamond maser operating at room temperature have an amplifier noise temperature, we estimate, of around about 2 Kelvin. So that's very exciting for low noise amplification applications. So I'd just like to conclude now. Most important point here is that fundamental science led us to the highest room temperature Q ever made. And that was in the aperiodic reflector resonator. That in itself was just a scientific curiosity. It was quite impractical to make, but we were very interested to see what the highest possible Q we could make was. But it did prompt the question, what could you do with such a high Q? It led us to the first solid state room temperature maser in the organic system with Pentacene and then in diamond. And the potential applications are room temperature, cavity, quantum electrodynamics platforms, quantum information processing, spin memories, and the ultimate low noise amplifier with very high signal to noise. So for example, we use low noise amplifiers everywhere, and we use them in, for example, magnetic resonance imaging. We could obtain an image with this low noise amplifier incredibly quickly and with far better resolution. So here's the Mars rover. With the reduction of noise, we have the most beautiful picture of the Mars rover. We can even identify the the individual grains of sound. And with the miniaturization possible, who knows, we might be able to make Mr. Spock's tricorder and jam many, many functionalities into a tiny little device. So, thank you very much indeed. And now I will stop sharing. Thank you. Okay.
Thank you, Professor Alford. Now the presentation is open for discussion.
It is. Have I stopped sharing now?
Yes, yes, yes.
Great. Okay, thank you. Thank you.
Hello, Professor Alford. It was an excellent presentation. I have one question. So it is related to the new quantum devices development in terms of Maser. What is the recent progress towards the quantum computing devices?
Okay. I think what we're interested in is that the Maser itself is a quantum device because of the way it operates. But I think the reason that we're interested in device applications is because it does offer this unbelievably low signal to noise. High signal to noise. We've got a very, very high signal to noise, and we have a very, very low phase noise. So one of the key problems in microwave and communications is jitter, and this is caused by phase noise. We estimate that the phase noise of this device will be extremely low. So at the moment, our feeling is that the most obvious application would be in low noise amplifiers because the noise floor is extremely low. But we do see other potential applications in quantum radar, for example, and also these room temperature Rabi oscillations are interesting. I'm not sure whether we would ever be able to use it for a room temperature quantum computer. I think the noise and the errors would be far too high. So I think that will always require cooling to very low temperatures. But there are certain devices that we do not need cooling with, for example, low noise amplifiers.
Thank you. Thank you very much.
Professor Alford, I have a question regarding the reflector resonator. What is the role of periodicity with respect to the dielectric laws?
Right. Well, actually, the aperiodic resonator was a piece of work that my colleague Jonathan Breeze did when he was modeling a Bragg resonator. And when he modeled the Bragg resonator itself, he found that the number of layers in a Bragg resonator, the Q factor would increase up to about 3 shells, 3 layers, and then it would saturate. And so why he tried to do an aperiodic resonator, I'm not quite sure, to tell the truth. It's one of these serendipitous things that happen. But what he did was to try to make the shells of the Bragg resonator not the same thickness. In other words, they were aperiodic in thickness. And that enabled him to calculate that if the resonator was made with layers of different thickness, that the Q factor would increase asymptotically. And that's exactly what we observed in the aperiodic resonator. So we obtained a Q factor of around about 600,000 for the aperiodic resonator at 30 gigahertz. And in the ordinary Bragg resonator, we obtained a Q factor of around about 200,000, again at 30 gigahertz.
Okay. So there is a question in the chat box. The complex and the real permittivity behaves differently with the frequency of field.
Yes.
When we make a measurement, which one is actually measured, complex or real?
We measure, when we make a measurement, we measure the real and the imaginary parts of the dielectric constant. But the one that we're particularly interested in is the imaginary part of the dielectric constant. And don't forget that we are confining ourselves to it's a good question actually, because we're confining ourselves to a rather narrow frequency range in the microwave region. The aperiodic resonator was at 30 gigahertz. Most of our measurements take place at 10 gigahertz, not very far away, but certainly not at very low frequencies, and certainly not at very high frequencies. So we are confining ourselves to a rather narrow spectrum of the field frequencies.
Any other questions?
Is it possible to have a long triplet lifetime? Like you said, it's not for Pandasine and Sapphire. It's not even possible to have a triplet state, so that will reduce the population inversion, something like that. So, is it possible to increase the triplet lifetime? So, by introducing some kind of metastable triplet state, something like that.
Yeah, that's a great question actually, and the answer is that we have tried in polymers. Or the organics, we find that we can't do that. We've looked at many different types of organic in order to achieve precisely what you've described actually, and we can't do it. We haven't found one that works yet, and that's why it was for that reason for the triplet lifetime, but also for the fact that in continuous wave illumination, we would almost certainly destroy any organic. So there were those two reasons: the triplet lifetime and the temperature stability. And we looked, and we decided that we would target diamond. But there are other inorganics that have quite long triplet lifetimes. For example, silicon carbide. So the silicon vacancies in silicon carbide, for example. And that's something else that we're about to start exploring. But it's a good question. We didn't manage to find an organic with this particular characteristic though.
All right, thank you.
Dr. Surendra was asking something.
My question was something related to the measurement of the quality factor. There appears to be huge difference between the theoretical quality factor and the experimental quality factor by several orders. What could have been the reasons behind that huge difference?
Yes, that's a good question too. The reason is, if you look at the theory, the Gurevich theory, the assumption is that there are no defects, no impurities in the materials that they look at. So, for example, they looked at sapphire, but they assumed that there were absolutely no defects whatsoever, and that's the key reason why there is this order of magnitude difference between a real material, which is always full of defects, and the theory. So that was actually where we started looking at these problems, going back to, in fact, we were working on that when Dr. Sebastian came over to the UK to work in our lab, and that was exactly what we were working on with my PhD student Chavi Orpi, who wrote some nice papers on that, and with my colleague Nebosha Lepjevich and with Jonathan Bree. So that was what started us actually on this particular road, to figure out what was the reason with the dielectric loss difference between the theory and the experiment.
Okay, thank you.
Any other questions?
My question, what about the stability of this device?
Yes, that's a great question. At the moment, the only thing that we have run this continuously for, I think we did it for an entire working day. So it's worked solidly for, I think it was 12 hours. There's once it stabilizes, it's mainly the thing that is going to change it is temperature. So once it stabilizes at a certain temperature under the illumination of the laser, then nothing else will shift its frequency. However, what I would say, and that is an excellent question, in the lab in which we were doing this experiment, we had to open the door every now and then, and we could see a shift in the frequency with a change in the temperature when we opened the door. And so from that perspective, the reason that takes place is, of course, there's a temperature coefficient of permittivity, which is related to the temperature coefficient of the frequency. And if we're changing the temperature slightly in a material which has quite a high temperature coefficient of permittivity, such as sapphire, which this was in, then we will get a change in the frequency if we get a change in the temperature. So that's the only reason that we're seeing a shift in the stability. Otherwise, the stability seems to be quite good. And certainly with an inorganic material such as sapphire, you can let a laser impact upon the sapphire for hours and hours, and it's perfectly okay. There's no problem. But the temperature coefficient is the issue that we are going to be dealing with.
Thank you.
Any other questions? So you can also type the question in the chat box. Okay, if there are no questions, I invite Sri Lakshmi, our MPhil scholar, to present the vote of thanks to Professor Alford. Sri Lakshmi, please.
Thank you, sir. Honorable dignitaries and most valued guests, it's my privilege to propose the vote of thanks on behalf of Department of Physics, University of Kerala, on the occasion of its Golden Jubilee celebrations. We want to express our heartfelt gratitude to our Honorable Speaker, Prof.Niel Alford, who has spared his precious time for us and illuminate us with his valuable knowledge. I extend our sincere thanks to all other distinguished guests who grace this occasion with their presence. I want to express my deep sense of appreciation to the organizing committee, especially our HOD, Dr. CBKS, Dr. Subodji, Dr. V. Biju, and also I would like to acknowledge the immense contribution of all other dedicated faculties of this department. Finally, I would like to extend my wholehearted gratitude to all the participants of this webinar. Thank you one and all for making this program a huge success. Thank you.
Thank you, Sri Lakshmi.